So homework number 6 is due. Tomorrow. You guys have a good 4-day-ish weekend? 3.5-day-ish weekend? Still want to be here. Hopefully today's not a total bust. Nice thing is in section 1.6 we're really just kind of reminding ourselves of all the different types of functions. Not all, I shouldn't say that. But starting our library of parent functions. Before I go in, because I'm just starting on linear, we go to quadratic and cubic and all this sorts of stuff. But parent functions. Did you guys use that wording last year at all, parent functions?
Yeah.
Okay. Do you remember what it stood for? What are parent functions? Kind of like the most basic, Brandon.
Like the original function.
The original before or pre-transformations, yeah. So it's kind of like the non-transformed function, kind of like at its core, if the basic one, etc. The nice thing is linear, we've totally talked about it multiple times, right? So, you guys tell me, what are characteristics of lines?
Straight.
Okay, has slope, first of all. We could say straight. I'm going to say constant slope, meaning you can choose any 2 points and you can find the slope, which is the slope for the entire graph. It's all the same slope. All the same rise, the same run. You guys should already know this formula by heart. I'm just going to do delta y over delta x. You guys know y2 minus y1 over x2 minus x1. Constant slope, it is straight, which basically just kind of describes the constant slope. If it was not constant slope, it'd be curved instead of straight. Let's see what else. I'm going to say usually. Lines have intercepts. But I said usually x and y intercepts. Question, when could it only have one and not both?
If it was either, it was just the horizontal line.
Yeah, if it was just horizontal, it would only have wouldn't have to hit, but would have to hit the y-axis, wouldn't have to hit the x-axis. Unless it was on the x-axis, that'd be a weird one. Or if it was vertical, it would only have to hit the x-axis, right? It doesn't have to hit the y-axis. We do have our special slopes. I think that's it for characteristics. It's good enough. But for our special lines, we do have our vertical, which is of the form x equals some sort of constant, right? Horizontal, y equals some sort of constant. Remind me real quick, what is the slope for vertical? What's the slope? No, not 1. Infinite slope, which we technically, in a shortcut way, say undefined. But it is infinite. And then horizontal. How fun is that? 0 fun, but whatever, at least you're still alive, right? Okay. Constant. A constant function is actually pretty much the same thing as the horizontal, just another way of naming it. So we'll also put y equals, I could say c is what they put down below, y equals d. Constant function is going to be a horizontal line every time. And then the identity function we know is y equals x, which has a slope of 1. Right? And y equals x is special for different things like reflections and inverses and whatnot, but we'll stop there. So we have the vertical horizontal, which has to do with slopes. We have the constant, which is a special name for horizontal lines, where y equals to the number. And then we have the identity function, where y and x are the exact same. We also say that this is directly proportional. Okay, but lines though, we've done that a lot, right? All right, let's start getting more excited. The squaring function. But who calls it the squaring function? Seriously, let's call it the quadratic. Characteristics. You guys know some stuff about them. What do you know? Yeah, you can say it's parabolic or it's a parabola. As such, since it's a parabola, what are some things that we can say?
this has to be a y-intercept, but not necessarily an x-intercept.
You could say that. We'll just say always y in, which means that there could be an x, doesn't have to be an x. For the parent function for y equals x squared, it does have a minimum at the origin, right? And similarly, once you start transforming quadratics, it's always going to have either a minimum or a maximum as long as it's a function. But the normal one, just a minute, yeah.
Does the slope constantly grows or decreases?
We'll say constantly changes, how about that?
Okay.
Technically for this one, for x squared, Luca, yeah, we would say increases or we would say grows. It's going to be kind of hard for some people to see that. Now some of you are like, whoa, what are you talking about? A parabola having slope? It doesn't have slope, only lines have slope. That's where calculus comes in. And I know, we're pre-calculus, but we're honors pre-calculus. How does a quadratic have slope? It's true that in order to have slope, you do have to have a line. So I guess my question is, how could we see lines in the quadratic? It's curved. It's not linear. True. So it doesn't have just one slope. It has lots of slopes. How could we see a line? What if that was just to put a random point, like right here? What's that slope? Negative or positive? Or zero?
Negative.
It's negative. But how are you doing that? It's not a line. No, but what's it doing? And it's going down, right? If you were riding this one, you'd have some velocity building, right? Here's how we can visualize the slope. Think about what we would call a tangent line. You're like, huh? You talk about tangents. It was just in geometry. There was like a circle, and there was a line that went off the circle, right? Now, this isn't a circle. We're not talking about a circle, but we are talking about a line coming off the curve. Question, what's the slope here?
0.
Zero. How can you think about it? Think of a straight line skimming the curve, right? Because you're going. Ooh. Now, it's not slope 0 for long. It's only slope 0 at one point. And then what starts happening? What direction are you going? Yeah. So it's going to be a negative slope of 0, then a positive slope. And why was I saying that Luca was right when he said that the slope was continuously or constantly growing or increasing? How is the slope growing and how is the slope increasing? There's an infinite amount, right? We can keep on going infinitely to the left and to the right. How do we read graphs again? What direction? Left to right. So as we go left to right, this is a negative number. Question. This negative number, is it higher on the number line or is it lower on the number line? Higher as in more on the right, right?
Yeah.
So say that's negative, I don't know, make up a number. What do you think? Like 3/1 maybe, or 4, not even that, maybe 2/1. Let's say that's -2. What could this one be? -1-ish? -2 to -1, that's increasing. How about -1 to 0? That's increasing more. How about 0 to 1? And then to 5 and to 10 and 100 and a million, right? So anyway, the slope is constantly increasing, and by slope, visualized by slopes of tangents. Now the big, or the first big, I'll say tangent lines to the curve.
Does that also mean you would draw like a bunch of tangent lines and then?
You could. Or you could also think about almost any function. If you zoom in, it'll look like a line. Which is why the window is so important, because not everything are lines, right? So we can't look at a zoomed in picture and know exactly what's going on, which is why we have to zoom out. But just in case you're curious, how to find the slope of a tangent line is actually one of the two huge problems that all of calculus is based on. But why is it a problem? You just find slope. How do we find slope? Rise over run. Oh, easy. I need 2 points. How many points does a tangent line have?
Infinite.
Infinitely many on it, but how many points that hit the curve? How many do I need? Struggle. That's why calculus was invented. All right, keep going. I can start going into all the transformations, but we'll do that, I think, in the next section. So, cubic function. He's a little more exciting. Ooh, I did think of one thing I wanted to do. You guys had a graph and a parabola, right? Can we just label real quick? It's increasing after the minimum, and it's decreasing before the minimum. It's increasing after the minimum, decreasing before the minimum. Question, I don't know if you need to write it, but what's the domain of a quadratic? Maybe we do need to write it. Go back to your graph.
All real numbers.
What's the domain? X is within all real numbers. What's the range? All real numbers?
No. X
No.
equal or
X
greater to
is
0.
greater than
X?
y.
Ooh. Y greater than or equal to 0. If we were to use interval notation, what would that look like? Bracket?
0,
0 to
comma, infinity,
50.
parentheses.
What would we say for lines? What's the domain?
Yeah.
Why am I saying usually all real numbers? Anybody think of an exception?
Because if you have the vertical, then
Is he going through lots of x's?
No.
Nope, he's just going through 1. So careful, he's the one exception. He's only going through 1. And what's the range? Forever high, forever low, right? Forever high, forever low, right? Forever high, forever. Okay, so usually. And what's the exception for him?
Horizontal line.
Yeah, a horizontal line would be the exception. For most lines. For most lines. Okay, let's see. I forgot about domain and range. So I think you good. Okay, what's his domain? What's his range?
All real numbers for both.
He's nice because domain and range are all real numbers. For the normal cubic function, the non-flipped cubic function, well, first of all, hold on. Cubic function. He's going to always have both x and y intercepts, right? Both x and y intercepts. Because he's not restricted. That's why his domain's all real numbers and his range is all real numbers. Second of all, for the non-transformed, we can say that he's increasing. How often? Remember, read it left to right.
Always.
Always.
Not.
Because he levels out, but only for a point. We don't really count him. If you want to make it super particular, I guess we could say from negative infinity to 0, and then from 0 to infinity. We could technically say ignore 0 because it's flat at 0, and you would be right. But we can also kind of say it's increasing always. But if you want to ignore that point for right now, since we don't know calculus, that's okay.
So you're not going to consider the 0 as a constant, not increasing, constant, increasing?
No.
Increasing,
Because to be constant, we have to have like a range of numbers. So at one point, we're not going to count it as. At least not for intervals. Not for intervals. In calculus, though, you're right, Luca. There, it's like a slope of 0. So we could say it's constant at one point, but we're only talking about intervals. So it's what we would call it for increasing, and since it's only increasing, we would call it strictly which means it's only doing one thing. It's not decreasing or constant. It's only increasing. Strictly, and we'll say monotonic. We'll see this one a little bit later, but monotonic, think monotone. People speaking in monotone, just kind of speaking around the tone. They don't ever vary. Same thing here. It's not really varying in the sense of it's always increasing. Can you guys tell what's going on with the slopes, though? What are the slopes doing? The function's always going up, but what are the slopes doing? Linear, constant, slope, quadratic, the slopes are always increasing.
Slope is decreasing and then it's increasing.
Because it's positive, but then it's less positive, less positive. Uh-oh, now it's 0, and then it goes positive again, right? So we could say like maybe 5 and 2 and 0, and then 2 and 5 and 10. So the slopes are decreasing and then increasing. So the slopes are decreasing and then increasing. Once again, not constant. They're always changing. Those little baby tangent lines are going to be always changing. But the slopes are going to be decreasing on, okay, let's do it the same way we did with the function. So decreasing and then increasing. Decreasing for x, what would you guys say? What would the interval be? Let's just keep them all open like we always do. And then increasing, oh, the slopes are going up. So we'll say from, can you guys fill in the second one?
0 to infinity.
He's stealing it. So the slopes are getting less steep to 0 and then more steep after 0. Before 0 is negative infinity, after 0 is 0 to infinity. We'll stop there. Question, do cubic functions have any maximums or minimums?
Yeah, but not in the parent function.
They could. I think that's what, yeah, they could, right? Have you guys ever seen the really skewed ones? They could have maximums or minimums. They don't in the parent function, that's true. But whether or not they have maximums or minimums, what do they always have? Do you guys know the point at which concavity changes? What that's called? No. It is at the origin. Whether you're here, there's a special point in between the two maximum minimum, or whether you're here, there's a special point in between. What happens to your voice when you are not monotonic?
It fluctuates.
When you're talking, it fluctuates. What's another way of saying fluctuate? Goes up and down. It has, or you have, inflection. Inflection is another word, another way of talking about it. Point of inflection. Inflection is kind of like changing. And the increasing isn't changing at 0, 0, but what the slopes are doing is changing. So we'll actually also say, I forgot the last one, there's a point of inflection. Luke is right, sometimes there are maximums and minimums. There aren't in the parent function though. In the parent function, there's a point of inflection which shows the concavity. Alright, so what else we have? If you think like a quartic, it starts to get kind of boring though, because then quartic, quintic. Quartic kind of acts like a quadratic, the normal one. X to the 4th, x to the 5th kind of acts like x cubed, it's just steeper. So instead of going on like all these different powers, let's kind of shift gears to the square root. And as you guys are graphing him, I think my first questions of the other ones were, well, it became, what is the domain and what is the range? So after you guys graph them, go ahead and just think on your own. What could I say is the domain? What could I say is the range? All real numbers, like the cubic? Restricted? How would you write them in intervals? I know today it's just a lot of teaching because we're not transforming stuff, not a lot to practice. Just getting stuff down, the basics, the fundamentals. You've been able to think through it? What would the domain be? What would the range be? the domain for me? How far left, Jesse? Yeah, it goes to positive infinity and how far, that's how far right, right? How far left? So 0 to infinity. Infinity, remember, always a parenthesis, and 0, since it's there, what would I say? Bracket. Yeah? Range. How low does it go? Yeah. And how high does it go? Yeah, that's funny. It's the same thing. Now, why algebraically, looking at the equation, looking at the square root, why does it make sense the domain is greater than or equal to 0? Do you remember domain problems in the first part of chapter 1? Square root. So let's remind ourselves real quickly. Just since we're talking about it, the rest of them haven't had domain problems except for a vertical line. That one had a domain problem. But on this one, we have to remember that whenever we have square root of x, we have to take whatever's underneath, set it greater than or equal to 0, which right now it's only x. It's the parent function. It's only square root of x. But as soon as that gets messy, then we have to think back to our domain problem. Let's see, what else is going on with the square root function? Increasing, decreasing, constant. What's going on? He's strictly increasing. Not for all real numbers, but that's okay. We could still say that he's strictly monotonic because it's for all the different values in his domain. So everywhere he is, he's increasing. But how is he increasing? What's going on with the slopes? He's increasing, but he's increasing. Yeah, it starts to level. And if positive numbers are going to 0 or are leveling and getting closer to 0 because 0 is flat, what does that mean about those slopes?
They're getting smaller.
Yeah, they're decreasing. And if you guys remember from section, I don't remember, something in chapter 1a. What is another way of describing a slope between 2 points? It was an application. Had something to do with motion. We said whenever it asks for mean slope, that was literally what was on the slide. 4 words. Starts with average. Average rate of change. If slopes have to do with rates of change, average, there are 2 points, like a secant line. Instantaneous, there's 1 point, like a tangent line. Anyway, long story short, if slope is rate of change or how fast, this thing's increasing, but I could technically say it's increasing since the slopes are decreasing, the rates are decreasing. I could say it's increasing at a decreasing rate. Or it's increasing, but slower. It's increasing, but slower and slower. So it's increasing, starts fast, goes slow. I'm not going to write it, but let's look at the cubic. What could I say about the cubic? It's increasing. Oh, I went forward, backward. It's increasing faster, right? It's increasing faster and faster and faster. It does slow down, and then it goes faster. The square root. It is increasing, but it's going to take it forever to get near as close as the cubic.
What do you mean the domain problem of the square root of x? Would it be square root of negative x problem? Because it can't be that.
Remember, x can be any number. So the problem is x when x is negative numbers.
Okay.
Does that make sense? So I say x has to be greater than or equal to 0 because x could be negative in and of himself. We don't need to have a negative root. Okay, you guys saw a second ago. Reciprocal. Here's another special one. 1 over x. Ooh, he has a domain problem too. What's his domain problem? we're going to start off talking about domain. Since we just did it for square root. Remember, when we have 1 over, the parent function is just 1 over x, nothing messier, but we know it can get messier. What can x not be? So since x cannot be 0, how could I write the domain in interval notation? Is there anything else that x can't be, or is it just one number that it can't be? Yeah, x can be like anything else, right? No big deal. X can be all the negatives, x can be all the positives. X can even be like 1/3, it'll just be really, really high. So how do I write it in interval notation? How far left? Negative infinity. To how far right? Yeah, I can't go past 0 or else I include something that's not allowed. How do I make sure it doesn't include 0? Bracket would say include. Open. If we want to be super mathematical, we could use the union symbol, but we haven't really gotten there, so we'll just use a comma. And then, as long as we don't include 0, we'll just say it's a positive infinity also. So everything but 0. And so we did the whole not equal to 0 when we were trying to study the domain problems. Yeah.
What's that called where it gets infinitely close to 0?
Horizontal asymptote. Is this one? And then we have vertical asymptote this way. Speaking of which, hey, range. How low can it go?
But that's not a function.
How low does it go? Negative infinity. How high does it go? Positive infinity. But why am I going to write positive infinity down here? Because it never hits 0. So technically, domain x can never equal 0, and then range, in this example, y can never equal 0 for the parent function. Sometimes the range changes a bit, but domain, we always have that problem.
Is a range problem too?
Mm-hmm. Technically, there's a range problem. But there's not really a nice way of solving for that. Horizontal asymptotes, there's the whole, you guys might remember from last year, the degree tests, the top and the bottom, which one's higher, which one's stronger. Anyway, we'll get there. Let's see, what's he doing? He's, increasing, decreasing, constant. How would you answer that? Remember, left or right? Yeah, he's strictly decreasing. So we can say decreasing. He's strictly monotonic, just in a different way. He's doing the same thing. Now remember, it's just within the domain, so we'll have to do the little intervals. There we go. He's strictly decreasing. He's strictly monotonic too, but in a different way. He's going down instead of the cubic, which is always going up. We say always because it's always in his domain. It's like, oh, obviously everywhere but 0, because 0 always doesn't exist. 1 over x. What's happening here? What's at x equals 0? What's at the 0 of the denominator? What's that called again? I said it a second ago. It is the y-axis, but it's an asymptote, and it's a vertical asymptote. Asymptote. There you go. And the nice thing is that actually translates in the sense of whenever we find the domain problem, whatever it can't equal is the placement of the vertical asymptote. That's always true. Besides that, go ahead, Luca.
Asymptote. Horizontal asymptote.
There's a horizontal asymptote at y equals 0. And I was going to talk about his slopes, but his slopes are a little bit more. I won't underline that one. Doesn't go with the domain problem.
And it's at y equals 0 because the x in the denominator
Is stronger than the top, and so whenever the bottom is stronger than the top, you always have 1 at 0. But that's the review for last year. Technically, the slopes, what are they doing on this side? Yeah. Now, you're like, wait, it's getting steep though. That's true, but it's getting more steep negative, so think number line like -2, -5, -10. Oh, it's going that way. So we say decreasing. But what's going on to these slopes? Also decreasing, but getting closer and closer to 0. Closer and closer to 0. I'm not going to go into physics right now. I could and kind of explain what this would look like in terms of motion, but let's kind of leave that for another day. Nice thing is, guys, look, we have one more. Which, in some ways, it's like, oh, that wasn't a lot, and in other ways, it's like, man, we're running down like constantly today. I know. Last one. Last big category, piecewise. We have a couple special ones to fit in. Piecewise functions. Why didn't I show you one picture? Because they're all different. Depends on the pieces. Depends on what's in them. But we can say, first of all, that's going to be defined by inequalities, technically could be intervals, in pieces, right? You could have like an h of x, a g of x. What letter we use? That's usually all. J of x? J is not used very much anywhere else. There we go. You have as many pieces as they wish. Just depends. But when I say defined by inequalities, remember there are inequalities that separate the domain into different portions, different intervals, and then define the function to be a particular piece. Define a function to be a particular piece. I can't tell you the domain. It just depends on the pieces. I wish I could. That's kind of like a case-by-case basis. Let's get everything all nice and lined up. So I can't tell you the domain, can't tell you the range, the exact same reason. Just depends on the pieces that you're given. We can review real quick in the calculator how to do it. Right? Graphing Calculator Handbook. I'm not going to go through the entire thing, but we do need the division symbol, right? So we would do something like h of x divided by, and then we'd have our parenthesis, and then we would have, let's see, what will we use to get our inequality? We would need our second math menu to get our less thans, greater thans, etc. If it's a sandwiched inequality, just help me out real quick. We use the ands, we need to go over to the logic. No, the test, sorry. We need to go over one. So we need to split up any sandwiches we have. But that's in your Graphing Calculator Handbook. You guys have that. You don't need that from me. Step function. There are two main, or at least I should say two specially defined piecewise functions. They're technically both piecewise. But there are little symbols that represent them. The step function can also be called the greatest integer function. That's another way of describing it. I know you guys saw it at least a little bit last year. It probably wasn't your favorite.
Because it's only at 1, 1, 2, and 0. And I feel
So like looking,
0.5.
there's a little flat line everywhere between 0 and 1. So 0.1, just round down to 0. 0.9, round down to 0. 1.1, round down to 1. 1.9, round down to 1. We always round down to the greatest integer that's involved in the number. Never round up. We only jump up when we hit that new number. So like 2, we jump up to 2, 2.1, stay at 2, 2.9, stay at 2, etc. I'll give you an example of that one in just a second. But the greatest integer, some of you can't see it, sorry. There are a few different ways of showing it, but the way that our book shows is with it like a double bracket. In case you can't see it. A little double bracket around that x. I'm not going to show you him defined as a piecewise because it literally is infinitely many pieces. Meaning, he'd have to say x greater than or equal to 0, less than 1. X greater than or equal to 1, less than 2. X greater than or equal to 2. Okay, that'd take forever. No, we're not going to do that. However, staple on my desk, thanks Noel. For absolute value, I am going to go ahead and show who he really is. There are these nice little straight bars, and we know, okay, put in a positive, stay positive, put in a negative, it comes out as a positive. We know what it does, but how do we write that algebraically? We say there are two different pieces. One, if x is less than 0, and 1 for x is greater than or equal to 0. 1 for x is less than 0 for negative numbers, and 1 for x is greater than or equal to 0 for positive numbers. Now this kind of, I don't know, it can be a struggle depending on how you view x. Who is x? Help me out real quick. Is he one number? No, he's like a blank space, kind of, right? He's a blank digit where we can just go ahead and plug in whatever we want. Could x be positives? Yep. Could x be negatives? Yep. So let's take the negatives. Let's say x is a negative number. Give me an example. Negative 5. Or negative 2, or negative 1. We'll say negative 5, first one I heard. What happens mathematically to negative 5 once I put him in there? Comes out a positive, but how do I show that with math? What turns a negative into a positive? Multiply by a negative. Now this is what's weird. Absolute value sometimes is negative x. Yes, why? When x is already a negative number. Negative a negative number, positive, right? But what happens if I have a positive number, like positive 5? Plug him in. He stays the absolute value is really just a piecewise, but he's hidden behind these two little straight bars, and you just memorized him for forever and didn't really realize who he really was. Now, kiddos, you're like, we're done. I just saw the next page. It says homework. What's going on in homework 1.6? Okay. I'm going to read directions. We're like, the bells come in sometime soon. Section 1.6 is either going to be really easy or really hard, right? Good news is 1.7 says transformation, so that's not really the point of 1.6. 1.6 says make lines, okay. Use your grapher to graph stuff, okay. Do function notation like plug it into stuff, okay. Sketch a piecewise, okay. Hey, it's kind of like our graphing calculator handbook. Sound good to you guys? It's literally just 2 quick pages. That one and that one, and I'm not assigning all of it. So it's going to be a little baby homework. Just please, please, please use it as a chance to kind of get familiar or refamiliarize yourself with how these functions move. But otherwise, it shouldn't be too bad. However, what's coming tomorrow? Translations, dilations, reflections. Yay! So if you have some extra time, maybe look ahead and be like, oh, I learned this once and I have to know it again. Question, Jessica. Good one. Group 2. Group 3. Wait. Second row, get them behind. Group 4.
Okay.
Thank you.
So you want the directions in the homework? That's right.
Yeah. Doesn't have to be every word. So like
percentage?
like the first one's like fill in.
Oh yeah.
Like that. Or like solve or something.
Okay.
Or like find domain. Just make sure. Is that good? Thanks, Christine. Welcome. Bye, guys. Poison around my right. Perfect.